Cool. So, first of all, housekeeping. I created your website. So it's there. It just means all the stuff is in a flat format. You're still going to have to use Canvas to submit your assignments. I would still recommend, if you need to communicate with me for any reason, then obviously Slack is the easiest, but email me if that doesn't work. Has everyone who's actually doing this course now got access to Canvas? I know you had problems, but I followed up and it should all be available for you now.
Yeah.
Cool, good. So if anything's missing from this or you need other stuff, let me know. The other thing is, if you do need to contact me, there is my office. So I realise that not everyone will know. I'm level 6, 656 in Gardley Wardley. Please drop in and see me if necessary. Remember, we have basically EMG 13 blocked out for you for an hour from 10 till 11. I'll be there from 10:30 onwards for any questions. That will be mainly useful for any coding type questions if you need me. I haven't put my telephone number there because I never answer my phone unless I recognise the name, so you're not going to get through. So don't bother phoning me. Seriously, just Slack me, it's faster. I just don't answer my phone. So, lecture 3. Now remember, next Monday we do not have a lecture. Next Friday we will have a workshop. The first workshop will be on functionals. So for next Friday I will put some information about prepping, but you need at this point a laptop with R Studio, and I'll tell you the packages you need. Just it saves time, you come in here, if you haven't got the packages, you're not ready to go. But plan on coming in and actually working through the problems. As I said, if you want to have a practice, the slides are already up there, start working through to make sure you're up to date. Okay, so, lecture 3. Today we are going to have a recap of multiple linear regression, just to make sure we're all at the same point. I'm assuming that most of you will have been exposed to this in a mixture of stats model inference and then stats modeling, but there's nothing wrong with a good recap to make sure we're all. So there'll be quite a bit of revision today, hopefully. So, multiple linear regression. First of all, we'll start with our data. Our data is going to be this form. We have P predictors, which we denote by X. And then we have a response variable, and the response variable is a quantitative variable. And we'll start by assuming it can take any value on the real number line. And our model is going to be that yi, the random variable yi, which is the response variable for the ith individual, is a linear combination of the predictors. Plus, I've got a noise term there. I have that epsilon I at the end. I'm going to assume that the epsilon I are IID. So that means they are identical, they all have the same distribution, and they're independent of one another. I'm going to assume that the expected value of the epsilon I is 0, and the variance of the epsilon I is sigma squared. So they all have the same noise structure. That comes from the IID. I'm not going to automatically assume normality on that. I haven't got a distribution. All I know of the distribution of the random variables, which are the epsilon I, is that they're independent, they're identical, and we know the first two moments. We know the mean and we know the variance. Okay? Here's exactly the same thing in the matrix form. So now I represent all my response variables as a column vector. So I've stacked them y1 up to yn. And I've represented all my predictors and an intercept by this thing called a design matrix. And the set of the design matrix is that each row is a subject, each column represents a predictor, or we have that first column of ones which represents the intercept. Now I've got a vector of my parameters in this model, which is the beta 0, which is the intercept, and then beta 1 up to beta p. And then I've got my final thing, I add my epsilon there, which creates the E, so I've typed that wrong, which is my noise structure. In this matrix form, now we've got the expected value of our epsilons is the bold symbol 0. So basically, your expected value of epsilons is just a column vector of zeros. And now our variance covariance matrix of our epsilons is a big matrix which is n times n. It's zeros everywhere, and along the diagonal you have sigma squared each point. This means that at this point, your noise terms with that matrix are uncorrelated. If we assume normality, they would also be independent. Remember that if two variables are independent, then the covariance equals 0. If two random variables have a covariance of 0, it does not mean they're independent, unless they have a normal distribution. So one of the reasons we love the normal distribution, showing two variables are independent is hard, showing two variables are uncorrelated is easy, and if you make that assumption of normality, all I have to do is show that the covariance is 0 and bang, I've got independence. Okay, so that's our setup. So before we go, let's go back and think about this model. So we talked about the other day about fitting a model. What we mean by fitting a model is we want to choose the parameters. At this point, this model has beta 0 up to beta p, our parameters of interest. They describe the relationship between our predictors and our response variable. And also we've got this extra parameter sigma squared. So this is a parametric machine learning regression approach. Highly interpretable. The whole idea is I'm going to take my data, I'm going to choose the parameters that best fit the data, and then I can use that for prediction. So the standard way of choosing these parameters, you can do it in numerous ways. You could do it in maximum likelihood estimation, etc. But what we're going to do is the least squares estimate. So we set up a heuristic, a measure of how well our model fits. So it's the norm squared. We take our observed data and we minus off our x beta, which is our model. And we're going to choose the value of beta that minimizes that, hence least squares. All you're doing is you go, what does my model predict this value should be of response? I take response, minus predicted, square it, add them all up. That is just the linear algebra form of that. That gets us our betas. It doesn't get us our sigma. How do we get our sigma squared? We estimate it by actually taking our estimated values of the beta. The hat over that beta indicates that we've estimated it. That is, we've taken our data and we have a sense of them values. So we look at the difference between our observed values, our fitted values, we square it all, we add them all up, and then we divide by the degrees of freedom. Now remember, the degrees of freedom, we've got to the point now, it is the dimensionality of the subspace that is orthogonal to our model space. What that means is, you observe this data, it's n-dimensional. That response variable is n-dimensional data, yes? And you're saying, I can decompose that into two parts. I can say, what part of that vector lies in a subspace that is my model? And what's the stuff that's left over that's orthogonal to that subspace? Your degrees of freedom is the dimensionality of that subspace of the stuff that doesn't lie within the model space. Or, the other way, the lies to children that we told you before is that we have n pieces of information to do this estimate. Altogether, I had to do p plus 1 calculations. I do a calculation for each coefficient plus the intercept. And every time I do a calculation, I lose some freedom, so I lose a piece of information. Them two statements are equivalent, yes?
You have p equals r plus 1, integrating weight for dimensions.
That's probably because I've copied and pasted and got it wrong. It should be p is, you got p, and then your dimensions is a p plus 1. So I think it should be n minus p, so I've got the thing wrong. Sorry, I'll correct that. I'll make sure I get it right. The problem is I had two notations and I was trying to mix them. And I got them wrong. I apologise. Now, we know that if the columns of x are linearly independent, then the least squares estimates are given uniquely by b hat equals x transpose x and minus 1 x transpose y. So you can take the design matrix and you can get those beta hats easily. So if I've fitted that model, there's some important questions I can start asking of that model. These are standard things that we might be interested in. First of all, simple question. The first one you might ask is there any relationship between the response variable and the predictors? You have this model. First thing is, well, is the model any good? Now, let's think about this. We have a parametric model, so we can put this in terms of asking questions about parameters. So our null hypothesis would be the simple one that says, look, all the coefficients, beta 1 up to beta p, so every coefficient except for the intercept are 0. So in the full model, I'm saying all these coefficients are important, they have a relationship. If at any point, if one of those coefficients is 0, if you think about it, it just says that that model, if we go all the way back to here, if at any point, if I can set one of these parameters equal to 0, then when the associated predictor changes, it's not going to change y. Make sense? It's the equivalent of the slope in the univariate. So our null hypothesis is that every single coefficient except the intercept is equal to 0, versus the alternative is at least one of them isn't. Doesn't tell me which one it just says. So this is the first basic question I can ask. How do we do that? We do that with an F-test. We take our total sum of squares and we take off our residual sum of squares. So let's think about all that. The total sum of squares says take every observation and see how much it varies around the mean of all the responses. So I'm taking no account of the predictors, I'm just looking at the response minus its mean. It's the variability of the response variables. The residual sum of squares is how much does each yi vary around its fitted value. So what's the variance explained once I take into account the model. So the first one is what's the variability in the y's. The second one is what's the variability in y's once I take into account my model. And I'm going to look at the difference between this. I can say, let's take the total variability, take off the amount, and look at the difference between these two variabilities. And then I describe that by P, which should be, and I will check that I've got my P's, etc. right, and the R's, should be basically the difference in degrees of freedom of this model and this model. Then I divide it by the residual sum of squares divided by its degrees of freedom. So let's think what I've done there. First of all, the nice thing about the sum of squares is they can be decomposed. We set them up to be orthogonal. So basically you can show that the overall total sum of squares can be divided into the sum of squares of the model and the stuff that's left over. Because these are designed in linear algebra to be orthogonal, there isn't any sort of cross product term. So what we've got here is the difference between two sum of squares that are orthogonal. So basically what you've got there is, under certain assumptions, a chi-squared distribution. What you've got at the bottom is sum of squares by degrees of freedom. That's another chi-squared distribution. If you take the ratio of two independent chi-squared distribution, you get an F distribution. So I can calculate this F statistic, but I can actually get a distribution for it. Under the assumption of normality, that would be a F distribution. What we're roughly doing in this is, if your model, if this was true, these two things would automatically both be estimating sigma squared. If the model, according to this null, was true. That is, if your model makes no difference, it's like you go, I've got one way of estimating sigma squared, fine. And someone comes along and goes, I've also got another way of estimating sigma squared. Hence, if the null hypothesis is true, I'm taking an estimate of sigma squared divided by an estimate of sigma squared. I should get 1. If the alternative is true, this will get bigger and bigger and bigger. This will go further and further away from 1. So your rough rule of thumb is, any point you see an F statistic, if it's getting further and further away from 1, it starts to say, I think the alternative is true, hence at least one of those coefficients. You could do this in a more advanced case. At the moment here, I am doing a multiple hypothesis of all these parameters. You can actually do it as easy as going, let's take the full model and let's look at a submodel. In fact, I can compare any two models that are nested using this sort of approach, where you do the sum of squares on one model and the difference of the sum of squares divided by the sum of squares of the largest model. So you can actually do subsets of coefficients as well. If you're not sure about all that, go back to your second year stats mind inference notes where we went through it in more detail. And I assume you also did it in stats modeling as well. Okay, next question we should ask is, okay, my model makes a difference, but do I need all the predictors? Could I have a subset of predictors? So we've got to now the question of model selection. So decide on important variables. Well, first of all, you might want a measure of how good your model is. So sort of measures you could do things like the AIC, the BIC, the AIC corrected or adjusted R-squared. Later on in this course, I'm going to go through these in more detail. But these are just measures of how good your model is. Okay? So just see them as a measure. You can take an individual model and you can get a number spitted out and it'll go, right, this model's this good, and then you can compare two models. You can also do things by looking at the p-values. But then you can go, well, how can we approach our model selection? And again, I'll do this in a lot more detail. I'm just sort of recapping what you should have seen before. So there's three classic methods of model selection. The first one is you start with the smallest possible model, which is just an intercept. And then you go to every one predictor, you add it in, see if it improved the model or not. You went to the next one, added it in. And you find the predictor that best improved your model, add it in. Now go and say, right, of all the predictors that left, add them in one at a time, see which best improves it, add it in. At some point, you're going to try adding them all in and nothing will improve, you stop. That's called the forward selection method. Backwards. Start with a full model, and you go, right, can I take a predictor out one at a time, see if it significantly makes the model worse. If one of them you can take out and it doesn't make the model worse, take it out, keep doing it. Finally, the mixed selection is you start with the small model, the null model, you add in, but every so often once you add in, you can actually look back and go, can I take something out? So you're sort of doing that stepwise. The problem with the first two is they're greedy and they don't get your model space. Let me show you a diagram to explain. So imagine we have three predictors, x1, x2, x3. And here's my full model. Yep. Now, if I have n predictors, or p predictors, I have 2 to the p possible models. So in this case, I've got 3 predictors, so I've got 8 models. Yeah. If I do the forward, let's say, let's choose one that I can't get to. Let's say this is actually the best model, hypothetically. But imagine that I do some sort of forward selection. I start here, and just by the nature of the beast, end up making this step here. Just so happens when it comes to the 3 predictors, this happens to be the best model. Once I make a step here with the forward algorithm, I cannot get to this point. It's a greedy algorithm, it will find that best route, but you lock yourself into a pathway. The same happens with the backwards. If I started here, and this happened to be the best model, and I step back here, I'm never going to get to it. The problem is I'm not exploring this space well enough. Now that's fine. The first thing you can do is you can actually do, we didn't mention, you can do an exhaustive. An exhaustive is, I'm going to look at every model, choose the best. The problem is that gets big too quickly. You know, the models we should be looking at should have hundreds of predictors. 2 to the 100 isn't going to fit. So you often use the forward or the backward or a mixture that sort of explores through it. If you really want to explore your models, there is things like, there's a package called GL-Multi that actually uses a genetic algorithm to explore model space. So you can actually do other ways like that. But you might then say, well, what's the difference between the forward and the backwards? Why would you sometimes use the forward and sometimes use the backwards? The classic one is often in some data sets, you have too many predictors and too little observations. Hence, you can't fit the full model. It's just not possible. You cannot fit a multiple regression if you have more predictors than observations. Okay? So sometimes in the data sets I look at, they get really excited. They come in and go, oh, we've got so much data. And I go, no, you've got so many predictors and you've actually got 10 observations. They go, but look, it's a whole gig of shit. But anyway. What about your model fit? So let's say I've done some model selection, I've got this model fit. You could do the one we said at the start of how models fit. But classical measures, the ones that most people out there use, are either R squared, which is you get your total sum of squares minus your residual sum of squares divided by your residual sum of squares. That is a classic one that's used in a lot of the literature for judging models. The other one you'll see is what we call the root square error, which is RSS divided the square root. These are classic measures that people use out in the literature. So I wanted to have a quick rant about being careful with these. Here's a beautiful warning illustration. What I've got here is I've got a data set and I have basically fitted increasing complexity of models. And as you can see, as my model gets more and more complex, I find that my R squared, which if you think about it, the closer to the 1, the better your model is. In this case, your R squared has gone all the way to 1, so it's almost a perfect model. And if you look at your root mean square, it's gone really, really low. So if you were going to do the blind, let's just use R squared, or let's just use RSE, this is the model you would choose. It's fantastic. So let me show you how I made this picture. Okay, you've got a minute. Talk to the person next to you. Explain to them what that R code does, and explain why my results are useless.
What does gather do?
Gather takes your data, which at the moment has a lot of models, and it converts it into a long form. So gather's good for taking wide data and make it into long data. So let's say if I had data that sort of went, Jono, coffee on Monday, coffee on Tuesday, coffee on Wednesday, coffee on Friday, had the numbers. Gather, now I'd have Jono, Monday, coffee 1, Tuesday, coffee 2. So it makes it into long form, so it's really easy to plot it. So gather and spread convert between them. Gather will take wide data and make it into, so you now have basically each row is a single observation, while spread will take single observations and spread it into a wide form. Highly recommend, if you don't know them, you go and get the R4 data science book. You go and learn about them, because a lot of your time is spent with data, taking it from wide to long and backwards again. Okay, so let's break it down. First of all, I set the seed. Why do I set the seed? Because I want to make my simulations reproducible. I don't want different results every time. Remember that if any time you're doing simulations in any language, not just R, set a seed. It makes it reproducible. Remember, all simulations are based on pseudo-random numbers. They look random, they're not. And the idea is you can repeat that randomization by setting your seed. First of all, I create my response variable, and then I create my predictors. And notice my predictors in this case are random noise. They have absolutely no relationship with my response variable at all. They are completely random. Okay? Then what do we do? Then it starts to get a little bit leap very quickly. Sorry, but we'll do this next week in the workshop about stuff. But this basically says, take the vector 1 to 20. So it goes 1, 2, 3, 4. For each number in that vector, I want you to fit a linear model of y on the first I rows. So do it on the first predictor, then the first 2 predictors, then the first 3 predictors, etc. I want you to do that. This says I want you to do it for every single number in this, and I want you to convert it to a data frame. Because once I got my linear model, I quickly grab glance. Glance gives me a little single row of a data frame, which is a summary of that model. The .id equals I means I'll have an extra column that tells you this was the first model, the second model, the third model, the fourth model. So I've now got this beautiful thing where I have a row for each model, and the models are slowly getting bigger in size. I did this because unfortunately it treats this as a character, and I wanted it to actually do it in numerical order. So this takes that column I and converts it to a number. That's what mutate does. Then I grab the columns where I've got the R squared from my data frame, the RSC, and the number of parameters. And then, so now what I have is I have each model, I have which model it was, the R squared, the RSC. But I want to put them on the same graph, so I just gather it. So I'll have, each row will be a model, and either the RS is this value, or the MSE is this value. And then shove it into a ggplot. Okay? By the end of this course, I want you to be able to do commands like that easily. I want you to have that sense of quickly producing that plot with that sort of tidyverse, functionals, etc. It takes practice. It takes deliberate practice. But what hopefully I can justify to you is it's worthwhile. That sort of quick purr is the sort of thing that for the first 20 times you do it will take an hour and you will hate me. The 21st it will take you 5 minutes and it will save you 18 hours. That's the idea where I want you to start doing deliberate practice on some of this R coding, because if you're going to do data science long term, you'll be doing this all the time. I can honestly argue do this all the time because I used commands almost identical to that last Sunday to do analysis of opioid dependency in people and looking at genotypes. So I absolutely can guarantee after this meeting I'm going to go and show some results that use the exactly code like that. So it is actually useful. The main take-home message of that is one, Jono likes doing really obscure leak code because he thinks it's fun. But the main one is there is no relationship between y and x, and yet we got this perfect model at the end. Don't blindly start using R squared and RSE. You are better than the rest of the world. Question 4, can we do prediction? So imagine we've got a new point from our thing, so we fit in our model, we've got it, and you come along with a new set of values, x0, and what you really like to do is predict your y0. Well, there's two things you can do. First of all, you can do a confidence interval for the expected value of y0. Think about that in terms, what you're saying is, if I had the whole population of individuals with that set of predictors, what's their expected value? It's a confidence interval because it's basically an interval estimate on a parameter. What's that parameter in this case? It's the expected value of a random variable. How do you do it? You take your predicted times by your fitted coefficients, plus or minus. Obviously, to do this step, I've assumed now some normality, or my data set was large enough that the central limit theorem kicked in and I could assume normality. Remember, the majority of papers out there in the real world use the t-test when they shouldn't. The majority of papers out in the real world that use the t-test when they shouldn't, it doesn't make much difference because the t distribution is particularly robust. This is how much that would vary. So this will give me a confidence interval for the expected value. Sometimes you don't want the expected value, you want just an idea of that random variable, how much it would vary. So now we call it a prediction interval because it's the range of values that a random variable can take. Because now we're talking about an individual, it will vary a lot more than a parameter. You know, people's individual heights varies much more than groups of people's heights. The main difference between these two things you should notice is extra 1. This is identical except for the 1 plus. This takes into account how much variability around the expected value individuals go. Potential problems. You've always called this assumption checking, but what potential problems could go wrong with all our stuff? Okay, non-linearity of data. Remember, we've assumed in that model that our data is a linear combination of the predictors. That's what I mean by linearity. But that might not be the case. So, how would you normally check? Well, there's two ways you check. If you had a univariate, a simple linear regression, you would look at your residuals versus your fit. Remember, your residuals is that distance between your observed and your fitted. It's called residual because it's the stuff, the noise that's left over once you remove your model. You know, that's what residual means, stuff what's left over. Also, as a gotcha, in multiple linear regression, not only should you do your residuals versus your fitted plot, you should also do your residuals versus each individual predictor plot. Just so you know that. Okay, there's the plot. Got some data. We're looking at miles per gallon on horsepower. There's your residual versus fit. It's a standard 1 out of R. Who wants to tell me what you should expect, and who wants to tell me what the interpretation of that plot is? Who's going first? Go on, Anthony.
Oh, okay. So you want random scatter above or below the 0
Yep.
horizontal.
So that's what you expect to see?
Yep.
Okay, Ben, what do you see?
It's not random.
No? What sort of pattern do you see?
It varies more as the, what is it, horsepower gets higher.
Yep. Yep.
So,
We're not looking at that bit yet. That's going to be the next one. So we'll save that answer till then. What other pattern do you see? You're totally right. You see this sort of spreading. Spot on. Ross, what else do you notice with that?
There's some kind of trend sort of thing, you know.
Exactly. There's a curve.
Yeah.
So it's almost like you go, I took off this model, I look what's left. If there's a pattern still there, your model's not good enough yet. You think about what we're trying to do, we're sort of at this point, we're going, I have this data, and this data is split into two parts, signal, noise. If there's still a signal in my noise, move it into the signal part. Or in other words, in here, you look and go, and you're all right, we've got this curvature, the lowest line on there shows us, we need a better model. We need something in that model to take account the curvature. That's all you're doing. You fit a model, you look what's left. If there's still a signal, improve your model. Correlation of the error terms is another problem. We assume the error terms were uncorrelated. If they're correlated, then estimated standard errors of estimators tend to underestimate the true standard errors. So if two things are correlated, you get this, basically when you're estimating how much they vary, you're not getting a proper understanding. So basically this says we've got better confidence intervals and prediction intervals narrower than they should be. Now the problem is, beforehand, when I was looking at that other problem, I did a test. We had that nice little graph. We looked at the graph, we interpreted it. This often doesn't have a simple test to do. Often this correlation is all about what we call a design assumption. It's about going back to your data and going, how did I get my data? Could there be some sort of structure in there that would mean that observations are correlated? Okay. Common causes of correlation. Clustering. The classic one. Clustering can be things like you're looking at the relationship between lung capacity and height. We all love that one. That's the F3C data set. But if I have twins or people from the same family, they will be correlated. A lot of work is done on mice, puppies, stuff like that in research. They've got to be very careful they don't do all the same litter or all the same highly related individuals. You've got to be careful with that. The other classic clustering is temporal, that your data is actually recorded over time and there's a temporal relationship. Two things closer together in time are more likely to correlate than further apart. That's why if anyone's done time series data, you don't just do regression. You've got this correlation structure you must take into account. Spatial. Things that are close together in space can also be highly correlated. If you know from your experiment you have the potential correlation because of time or space, or in the case of clustering, genetics, things like that. Put it into your model, take it into account. Things like GAMs, GEEs, mixed effects models can be done to do this. Probably going to have a look at GAMs when we get to our splines type stuff, so you'll get some of it that can take into account. The other thing we've assumed is that constant variance term. So, it's your time to shine now, because in a second I'm going to, how can we test for constant variance? Well, we now look at our, you can look at your residual versus fitted. Often in R we look at the square root of the standard. Here's our fitted. Ben, what do you think of this plot?
What? Homoscedastic, is that what you statisticians call it?
That's what we call it, homoscedastic. Since you did the classics, that should usually the one person in the room who can say that word and not actually freak. Yeah, what we normally expect to see is as the fitted values go, we want roughly the same amount of variability. As you go across, in this case, we've got an increased variability. That single sigma squared is not good enough. We need to take it into account. Just as a recap, I assume you've done this, but ways you could deal with that, you could do a transformation. First thing, log your response variable. Harder to interpret, but it often gets rid of that problem. The other one, if you've not seen it before, how many people have seen weighted least squares? 1, 2, 3, 4, 5, good. The idea is if you know there is this non-constant, what you can do is you can adjust, and instead of having that big matrix with zeros and the diagonal is all sigma squareds, you can basically change that. What we do now is we have an n times n weighting matrix W, which has weights on the diagonals and zeros elsewhere. The nice thing is you can reformulate that. You take this diagonal matrix and you take the square root of it. So basically you look at your matrix and you just replace the diagonal weights with the square root of the weights. And then you pre-multiply your model. So this, if you think about it, is exactly the same model we saw before. Y equals x beta plus e. And I just pre-multiplied by this weighting matrix. I'm not going to go through mathematics, but you can basically still see that beta hat is x transpose x to the minus 1 x transpose y. All we've done is we've shoved in some stars because now we've basically got our adjusted. Basically, instead of before we had just x, we've got w minus a half x. Yep. So you've just taken your data, you just transformed it into this new weighted space and redone everything in the same format. For those who've never seen it done in R, you've probably never seen it because it's almost trivial to do. In this case, the data was done, I knew the weights I could get by doing 1 over the x. So you can pass in a weights matrix. So you pass in a vector of weights for each observation. Now, I did the same plot, you can see now it's looking much better. It's just weighted automatically. So. Influential points. Let's remind ourselves what that is. Every so often you will get a point that sticks out. And we care what it's doing when it sticks out. So the worst case scenario is this. Here I've got some simulated data, and here's my influential point. The complete line is the line of least squares when I don't include that point. The dashed line is the line when I do include that point. So there's two things to think about an influential point. First of all, how far is it away from the rest of the data in terms of predictors? So in this case, you can see all my stuff is over here, and this is a long way away. This distance is called leverage. It's how far away you are from everyone else. And you have leverage in your high dimensional version as well. This one's just a nice simple x. So this point has high leverage. It's also got high, large residual. So it's actually having an effect. Can you see how that line gets dragged up here? It's an inferential point because it's changing the coefficients of your model. You can see this over here. This is the one that actually R produces. What it does, it gives you every point. It gives you your leverage. It gives you your residuals. So you can see this point has high leverage and a high residual. But also it calculates the Cook's distance. The Cook's distance basically goes how much do your estimates change? What's the distance between your estimates with this in the model and not in the model? And it produces little contour lines. So you see this one is over here. These contour lines here, this is for 0.5 and 1. Roughly anything beyond 1 Cook's distance, you say, this point here is changing your model. So what do we do if it changes your model? You go back to your collaborator. You say, that data point, is it right? If it's wrong, and they record it wrong, change it, write down that you changed it so everyone knows for the world when you do your reproducible research, that's fine. If it's not wrong, it stays there. When you report the results, I'd report the results with it in and with it out and say, this is an interesting question for us to follow up. What you don't do, unless you get paid enough money, is remove that data point. This is interesting science, this data point, or it can be. Make sense? Remember, interesting data science is all about influential points. We have penicillin because a guy didn't throw away his results that went horribly wrong. You know, it wasn't Florey, it was the guy beforehand, and he basically was trying to grow up bacteria. He'd got mold on his thing that all died, and he was about to throw it away, and he went, I wonder why they died. So, influential points are important. The other scenarios you can have. Here, we have a small residual with this point, but large leverage. It's now here, and you can see it's within the contours. It's saying, yes, you'll still be worried. It sticks out from everyone else when it comes in terms of predictors, but it's not changing your model at all. So you still go back and you look at it and say to your collaborator, could you have written that down wrong? This one, we've got a large residual. It sticks out a lot, but it's not got high leverage. It's contained within it, just sticks out a lot. And you can see it's moving this model, but it's not huge in a large amount. Again, you look at it, you go back to your collaborator and go, could you have recorded it wrong? Any point that sticks out, you just want to go, why? Is the thing I'm not taking into account, or you record it wrong? And then finally, small residual, low leverage is basically a data point. But there's your... Okay, collinearity. Let's finish with collinearity. Collinearity is the case where you have two predictors that are highly correlated. We call it collinearity. The problem is that they're very correlated, and this can mess up your results. And it can cause the standard errors of the coefficient estimates to grow. Let me give you an example. This is a credit data set. So what we've got here is we've got a data set that is looking at the relationship between, in this case, we're going to look at your income, your limit, and your rating. Actually, we're going to look at your balance, limit, rating. So limit is, in bank loans, is the limit they put on the amount you can have. Your rating is how good a credit risk you are. Okay? So if you stop and think for a second, do you believe if you're a good credit risk, you're going to get a higher or lower limit? Higher, exactly. You know, if I think you're going to give me the money back, I'm going to lend you more. If I don't think, I'm not going to lend you much. So these two things are highly correlated. Here's the actual plot. You know, whenever you get data, stop, think about the relationship, confirm the relationship with looking at plots. So our stupidity was they're highly related, and you can see they're highly related. This is a problem when we try and put them both in the same model. Let's do that. What I've got here is the first model is trying to predict balance using age and limit. And the second one is now trying to predict balance using ratings and limit. What I want you to look at is these numbers here. This is the standard error of this. So first of all, limit here, you've got your 0.173, but notice how small that standard error is when it's on its own. It's quite precise, it's quite happy. As soon as I introduce ratings, suddenly the standard error is a magnitude more, the amount of variability. And all I did was change one predictor. I took a predictor here, which is significantly done, and basically also this one, notice limit is also significant. If you had this model, you'd go age and limit are good predictors of balance. you now introduce this in, and suddenly ratings is a good predictor. Limit is no longer a good predictor because the standard error has now got large, hence this is no longer a significant t-value. And it sort of makes sense because you're not getting any extra information. It's almost like going, seriously, you saw the scatter plot. If you give me rating, it's almost like I got limit for free. So you say, if you don't give me rating, limit is really informative. Once you give me rating, you're not giving me any more information. Now this was easy to do in this particular scenario because we could see that scatter plot. But now you've got 1,000 predictors. So you've got 1,000 choose 2 scatter plots you need to look at. It's going to get hard really quickly. So instead we have a standard way of doing it. We have a thing called the variance inflation factor. Basically, it's the ratio of the variance of our coefficient when I fit the full model divided by the variance if I fit it on its own. I'm not going to show this, but you can actually prove the smallest possible value is 0. And rule of thumb is any VFF greater than 5 indicates problems.
It says 1. But you said 0.
1. I meant 1. Sorry. Here's how you do it. It's actually built into the car package. So what I've done here, just in case you've not seen this before, if you see something like this, this says there's a function called VIF, colon says it's inside the car package. You could have gone library car and then just VIF, but sometimes, because I'm being lazy and I can't be bothered to type in library car, I just go car, colon. Okay? The car is the companion to applied regression. If there's any of this stuff and you're not sure about it, there's a really nice book by John Fox called The Companion to Applied Regression, which is great for all that sort of like start with linear regression and adapt it to get all the other stuff. So I fit this full model here with all 3, and then call this, and it will do the variance inflation and spit out like this. And what you can see is age is no problem, but limit and rating are basically collinear. It's one or the other. You go back to the collaborator and go, right, which is the predictor you want? I can't have them both in this model. Or, we'll see later, you could do what we call PCR, principal component regression. You do principal component to make all your things now linear dependent because you've got orthogonal principal components and use that as predictors. Cool. So that is your recap. Hopefully it was all old stuff and you could just feel comfortable in that familiarity. Monday we have no lecture. Wednesday I'm going to start doing classification. I'll do a recap of logistic regression and then we'll go from there. We'll start doing ROC curves, stuff like that, confusion matrices. Next Friday we'll be here, bring your laptops, I remind you, we're going to start learning how to use functionals. Get any questions, either come and talk to me now or talk to me on Slack. Other than that, have a really good long weekend. See you all next week.